Then let's invite Professor Kevin to discuss about improving video super resolution with enhanced propagation and alignment. So Prof. Kevin is a Nanyang Associate Professor with the School of Computer Science and Engineering at Nanyang Technological University, Singapore. He is also an Adjunct Associate Professor at the Chinese University of Hong Kong. He received his PhD in Computer Science from the Queen Mary University of London. He is the recipient of the 2019 Nanyang Associate Professorship from the NTU. He is recognized by inclusion in the AI 2000 Most Influential Scholar annual list. His research interests include computer vision and deep learning, with a focus on image and video restoration, enhancement, and manipulation. His journal paper on image super resolution was selected as the most popular article by PAMI in 2016. He serves as an associate editor of IGCV at PAMI. He also served as the area chair of CVPR 2019 and 21, BMVC 2018 and 19, and ECCV 2018. He has co-organized several workshops and challenges at major computer vision conferences. So let's invite Kevin. Yeah.
Thanks, Wei. I would like to share the screen. Okay, 1 second. All right, thanks for the kind introduction. My name is Chen. I'm from Nanyang Technological University. So good morning to those who are attending the conference in New Orleans, and good night to those who are at the same time zone as me. So I'm from the MM lab of NTU. So my lab has been developing many algorithms for image restoration, video restoration, and enhancement. So our previous algorithms like SRCNN or ESRGAN have been incorporated into a library called MM Editing under Open MM Lab. So this library basically contained a number of algorithms for image editing, image enhancement, and restoration. So today I'm going to share some of our research work on improving video super resolution, and basically by using enhanced propagation and alignment. Okay, so basically let's look at what is video super resolution. Maybe most of you know about image super resolution. For video super resolution, it has an additional temporal dimension, and therefore it will be harder than image super resolution. So the goal is whether we can exploit the complementary information from other frames to improve the resolution of current frame. So the key challenge here is to how we can gather the information for the reconstruction, and that would involve how we align frames, which can be misaligned because of the object motion, and how we propagate the information from distant frames to the current frame. And that's the key challenge. And the second challenge is how we can cope with diverse and complex degradation, especially when we want to address real-world scenarios. So this is a typical way that we perform super resolution for videos. In general, you gather a number of frames in a local window, and then you feed it into your network, and then you get the results. So this is a very simple and naive way to perform video super resolution. So most assistant work basically rely on this kind of sliding window framework, whereby you apply a local window, and then you try to restore the frames within the window. So what happened here is that your network couldn't reach distant frames to gather information because you only have limited extent in your local window. So that's the problem. And to solve that, you could use recurrent framework where you basically propagate information across the whole video sequence. But that would involve a lot of design choices. For example, how many frames that you need to propagate, and how do you design the propagation component. That remains an open problem in video super resolution. So this is our solution. What we tried to do last year is to examine all these components carefully and systematically and design a simple backbone that has a good trade-off for performance and efficiency. So what we found out is that in order to perform good video super resolution, you would need effective propagation and alignment. So these propagation and alignment are the two key elements to achieve effective and good performance in video super resolution. So we come up with the framework which is called Basic VSR, and in 2020, also last year, we proposed an improved version of Basic VSR called Basic VSR++, and we participated in the entire competition, and we got 3 champions using this method. And in this conference, we present a paper for Basic VSR++. And the 2 main components that we propose in this paper is a second-order grid propagation that I will explain later, and flow-guided deformable alignment. So these 2 components helped to perform better propagation and frame alignment that helped to achieve very good performance in compared to previous methods. So if you look at the graph here, basically, our method last year achieved a very good trade-off in terms of performance compared to UDVR, which is another very popular framework that we proposed in 2019. And the latest method here, the Basic VSR++, basically surpasses all the previous methods in terms of runtime and also restoration quality. And another work that we are going to present in this conference is Real Basic VSR. So in this paper, what we want to achieve is to cope with unknown degradations in real scenarios. So the main challenge becomes how we could balance between detailed synthesis and also suppressing artifacts due to unknown degradations. So I'll talk about that later. And I will also talk about how we can improve training efficiency when we try to train a video super resolution model. So all these methods, the 3 methods here have been incorporated into ML editing. So you can check the code out there. Okay, first, I will talk about Basic VSR++, basically how we can improve video super resolution with enhanced propagation and alignment. So this is the overview of our model. You can see that we have inputs here. This is the input sequence, and this is the desired output sequence. So at the beginning, we will use some residual blocks to extract shallow features from the input sequence. And then we will have a so-called second-order grid propagation to distribute information back and forth, so that we can combine the informations from different frames for the restoration. And within each block here, we have a component called flow-guided deformable alignment. So this alignment components basically help us to align those misaligned frames so that we can aggregate the information for reconstruction. So this is basically the main idea of our Basic VSR++ framework. Okay, let me first talk about the second order grid propagation. So to enhance the robustness of propagation, what we do is that we relax the assumption of first order Markov property in Basic VSR. So in Basic VSR, basically we only take the previous frames to combine with the features of the current frame for reconstruction. But in Basic VSR++, we allowed an additional connection, basically a second order connection, realizing the second order Markov chain. And with this relaxation, information can be aggregated from different spatial temporal locations, improving the robustness as well as the effectiveness in occluded and fine regions. And for as for grid propagation here, what we did is that instead of propagating the features forward and backward, we do this multiple times back and forth, okay, in an alternating manner. So as indicated by this diagram here. And through this propagation, the information from different frames can be revisited and adopted for feature refinement. And compared to our previous model, basic BSR, which propagate the features only once, the grid propagation over here repeatedly extract information from the entire sequence and therefore improving the feature expressiveness. And you may argue that, okay, this is more complicated than basic BSR, but thanks to the enhanced propagation and the alignment that I will introduce later, this model actually helps us to save parameters because of the effectiveness. And in fact, this model surpasses our previous model by a significant 0.82 of decibel in PSNR, given the same number of parameters. So the next thing I would like to talk about is flow guide deformable alignment, which is another component that we propose for basic BSR++. And to understand that, then we need to know about deformable convolution for alignment. And this has been adopted in some other previous methods like TDAN or UDVR. So what deformable alignment performs here is that it assumes that we have two frames. One is the reference frame, and another one is its neighboring frame over here. And what it does is that we will concatenate these two frames together, and then after some convolutional layers, we will obtain the offset map, okay, which is shown over here. And then this offset map will be used for the deformable convolution to sample different locations for convolution. And with that, what we get here is that we will get a line frame from this neighboring frame, okay, because of the convolution. So in other words, the neighboring frame is warped to the reference frame at the feature level based on offset. All right, so this is the typical deformable alignment. And for more complicated design, for example, in UDVR, they introduce a pyramid of deformable alignment to perform a better alignment. So in our basic BSR++, we actually redesigned the whole framework over here. So we found that deformable alignment is effective, but it is unstable for training. So what we try to improve is that why not using optical flow to have the learning of the deformable convolution offset. So in our current framework, what we do is that we will we will get optical flow, okay, using SpiNet, and then we will use optical flow to warp the previous frame. Okay, basically we warp the features to the LR features over here, and we concatenate them together. And this concatenation, after going through some convolution, we will get the residual offset instead of the DCN offset directly. We get the residual offset and add it back to the optical flow. And that will give us the DCN offset. And that DCN offset will be used for DCN block to perform deformable convolution. So the good thing about this framework is that we use optical flow as the base offset. And this base offset helps us to mitigate a lot of burden in our estimation over here. We just need to learn the residual offset for the DCN. And it is the offset learning. And the fact that we only learn a small deviation, okay, this small deviation in this residual offset stabilizes the training. And in addition to that, we also estimate a mask over here, which is attention mask. That helps us to provide flexibility on masking which features are important and not important when we perform the offset learning. So the whole framework here basically helps the alignment a lot. I will show some results later. So here I show the ablations, and basically the flow guided deformable alignment, the second order propagation and grid propagation, they each bring more than 0.1 decibel of improvement. And all in all, they provide over 0.91 decibel of improvement over the baseline. And here I show some visualization of the result. So without second order, we get a restoration result like this, but with the second order propagation, we get a much sharper result. And here is another example that shows the benefit of grid propagation. So without grid, we get the result like this. And with grid propagation, we get much sharper and better restoration. And this figure shows the benefit of using flow-guided deformable alignment. If you perform alignment by using optical flow to align the two frames over here, if you look at the features are pretty blurred. Okay, so that means they are not well aligned. But if you apply flow-guided deformable alignment, you can see much sharper features when we warp the features of this neighboring frame to reference frame. So that indicates a much better alignment between features. So here are the results. Basically, here we assume some blur input, and this is the restoration result. And you can see that only our method can recover the stripe patterns. And this is another video that shows how we can better recognize or restoring the carpet. All right, so you can find more results in our paper. And what we have done earlier is that we only apply this basic BSR++ on the task of super resolution. But in fact, this framework is generalizable to other restoration tasks, for example, deblurring or denoising. But here we need to make a small make some changes to the framework. So in super resolution, we basically assume that the input size is smaller than the output size. But in other restoration tasks, we have the input size and output size identical. So to basically to suit the framework for this kind of for other restoration tasks, what we did is we downsample the input images with stride convolution if the input size equals to the output size. So this is a very simple modification. And the downsampling factor is selected based on our requirements. So if the downsampling factor is larger, then the frame will be faster. And if the downsampling factor is smaller, then we get better performance, but it can be slow. So here we show the results on basically quantitative results of super resolution. Overall, we get more than 1 decibel improvement on this data set with 4 over previous best method, and get an entire 2021 champion. So you can see that the runtime actually is very competitive compared to existing methods. Yeah, it's very fast. And on other restoration tasks, such as deburring, denoising, and also compressed video enhancement, we also obtain the best results. Yeah, we are carrying the state of the art across many methods. Okay, here we show the qualitative results for deburring and denoising, because this is for super resolution. Yeah. Okay, so basically, in summary, for this in this study, we propose two novel components. One is second-order grid propagation that allowed us to propagate features more effectively across long video for restoration. And the second component is flow-guided deformable alignment that allow flexible alignment with motion guidance. And we also extend our framework so that it can work on more video restoration tasks. And this can be done by just introducing a very simple extension, which is strider convolution for efficiency. And we get, let's say, 40-hour performance on many restoration tasks. Okay, so that's the first work on basic VSR++, and you can try that on MM editing. And the second work, which is also another paper that is accepted in this conference, is we call it real basic VSR. So what we did here is that we try to investigate trade-off involved when we try to train a model for real-world video super resolution. So when we say real-world video super resolution, what we meant here is that we do not assume any known kernels or downsampling kernels, and we need to deal with unknown degradations in the wild. Okay, this is a more challenging and more difficult problem compared to non-blind super resolution. Okay, this is totally blind super resolution, and you know that. So it is a hard setting, but the more maybe the overlooked question in this problem is that when we train recurrent networks for this kind of real-world super resolution, it actually requires a lot of computational resources. And there aren't any studies out there to basically examine how we can save, how we can cut those redundancies when we try to train this model. And of course, there is no diverse data set out there for evaluation. And in this study, we try to address these problems. Okay, first thing that we propose in this method is image pre-cleaning. So this is a very important mechanism that is required for real-world super resolution. So our observation is that in non-blind settings, when we use more frames, when we do more propagation, then the results will be better. But in real-world settings, if we propagate frames or propagate features from distant frames, then artifacts are amplified with more frames. So if you look at the examples over here, so if we are dealing with non-blind VSR, where we know the kernels, when you use more frames for propagation, then you get very good results. But under real settings, when you use more frames, those artifacts from other frames will be propagated into your current frame and actually hurt the performance. So the reason is that the networks are unable to distinguish the high frequency details from artifacts. So that would exaggerate the artifacts when we use a longer propagation. So that's the problem. So the objective of image pre-cleaning, the cleaning module over here, basically is to suppress the artifacts in the input sequence before we send it to the propagation network. Okay, so this is a very simple idea. So just need to introduce a cleaning module over here. So that will make our framework into two-stage. First, you perform cleaning, and then in the propagation network here, you will perform detailed synthesis. So training the cleaning module is very simple. Basically, you just need to introduce cleaning loss. So in the cleaning loss, you would use a low resolution ground truth to sort of to train the module. And then the loss can be based on a simple MSC loss. And that works pretty well in practice. and you will find that it's essential for removing artifacts. So if you look at these examples over here, without claim loss, you get a result like this, and with the claim loss, we get much better results. Okay, and that is the first trade-off. Basically, how we trade off between the propagation, okay, by using a training module. So in the subsequent trade-off, what we examine is that whether we can make the training faster and more effective. So when we deal with real-world super resolution, real-world video super resolution, we basically need to train the model with a lot of synthetic degradation. Okay, that basically translates to using a longer sequence to train the model, and we also need to use larger batch size to stabilize the training. So if you want to cut down the training time, then you need to use short sequence and small batch size, and that would hurt the performance. So that is a trade-off over here. How to improve the performance yet using short sequence and small batch size. So our approach is like this, okay? It's simple. So instead of feeding the whole sequence, like as in conventional training mechanism, so what we do here, we only feed half of the sequence to the model, to the training process, and flip the sequence so that we can make it longer, okay? We flip the sequence to make it longer, and that would have the same length as in the conventional training process, but now we reduce the CPU load, yeah? And to compensate that, the loss of other frames, what we do here is that we increase the richness of the degradations by introducing different degradations or synthetic degradations to each frame, okay? By using, basically each frame will take different degradations. So that will increase the diversity of the training samples. So that is our final scheme, and it works pretty well. From our study, it can reduce up to 40%, basically increased 40% of training speed, okay, without sacrificing the output quality. So you can see the details numbers here, and you can see that basically the results are still very good. Yeah. Okay, and the third and final trade-off that we study in the paper is about the batch size versus the sequence length. So when you try to do the training, you have two options. So, and not bursting the memory. So the first option is to increase the batch size as much as you can, or you can increase the length of the sequence of your training. Basically, the length of the sequence to perform the training. So you cannot do both because you have a limited budget for your memory. So you can either choose one. And our finding shows that you should go for longer sequences rather than larger batch size when you try to perform, when you try to train a video super resolution network if your resources are limited. And that will give you better performance. Now you can look at the details in our paper. Okay. And lastly, we introduced a video LQ dataset. Basically, we collected a number of 50 low-quality videos from diverse scenes for evaluation. Okay, and you can download the dataset from our website. Yeah, I will skip this part. We get better results. Okay, I'll skip this part as well. All right, now you can see with our model, you can restore better, you can get very good results. Despite that, we do not know the degradation. So in summary, to train real-world video super resolution model, it could involve various trade-offs like the detail synthesis and artifact exaggeration, performance versus training time, batch size versus sequence length. And in this paper, we study all this trade-off and provide an answer. Okay, you can study our paper, and here I provide the links to the code to the respective papers and to our website. Okay, before I end my presentation, I just want to make a short advertisement. We are going to have a workshop called a BP workshop, okay, Mobile Intelligent Photography and Imaging Workshop in conjunction with ECCV 2022. And in this workshop, we organize 5 challenge tracks, okay, that emphasize the integration of novel image sensors and image algorithms. I will show the tracks later. And for this workshop, we also invited a number of very cool academic and industrial speakers to share their work with us. The challenge have started. Okay, we have 5 tracks here. Basically, how like for this one, RGB or top depth completion and Fury mosaic tracks, and how could you fuse the RGB-W sensory information. And that's another track on under display camera image restoration. There are many participants now, but if you're interested, you can still join the competitions. And we gave very good awards and prizes. So the first place will get 1,000 USD, second place 800, and third place 500. Okay, the challenge has started and is going to end in 20th of July. And we also accept papers. If you have papers, say, I don't know, rejected by ECCV, maybe you can try to submit to our workshop, and the deadline is 8th of August. All right, that's all from my presentation. I'm open for questions. Thank you.